Good day everyone. The topic that we want to discuss is the separately excited DC motor. The presenters are Yuan Xi, Xuan and Chian. In a separately excited DC motor, a separate supply is used to excitation both the armature coil and the field coil. In the case of a separately excited DC motor, the main supply is given separately to the armature and field windings. The major distinguishing fact in this form of DC motor is that the armature current does not move across the field windings, as the field windings power from a separate external supply of DC. Now we can see the equivalent circuit that we show in the slide. The left side of the circuit is the field windings, which is stator part, while the right side of the circuit is the armature winding, which is rotor part. Next, we will look at the equation of voltage, current, and power. For the field winding part, we have the equation of Vf equal to If times Rf. While for the armature winding part, we have the equation of Vt equal to Ra times Ia plus Ldia over dt plus Ea. Since Ldia over dt equal to 0, so the Vt is equal to Ra times Ia plus Ea. The equation of back EMF, electric torque, power, and the speed of the machine as shown in the slide. From the equation above, we can conclude that by increasing the Vt, the Ea will also increase and will result in the increasing of speed machine.
Hi and a very good day to everyone. Now I continue to talk about the torque speed characteristic of the separately excited DC motor. When the load increases, the output torque required to drive the load will increase. Hence, the motor speed will slow down. Consequently, the internal generated voltage drop, which can be shown by the formula Ea equals to K phi omega m. Then the armature current in the motor will be increased according to the formula Ia equals to Vs minus Ea divided by Ra. So, from the formula T developed equals to K phi Ia, we can notice that as the armature current increases, the developed torque increases. And finally, the developed torque will be equal to the load torque at a lower mechanical speed of rotation omega m. To simplify it, we can see the relationship at the bottom part, which show that when the mechanical load increase, the speed motor omega m will be decreased, and the armature current Ia and the torque developed will be increased. In general, three characteristic curves are considered for DC motor, which are developed torque versus armature current, speed versus armature current, terminal characteristic, which is the speed versus developed torque. These characteristics are determined by keeping following two relations in mind, which are Ea equals to K phi omega m and also the T developed equals to K phi Ia. So, for torque versus armature current, we just use the formula T developed equals to K phi Ia, where the developed torque is directly proportional to the armature current. Then, for the speed versus armature current, we substitute the equation Ea equals to K phi omega m into the equation Vs equals to Ea plus IaRa, and then we rearrange it, we will get omega m equals to Vs minus IaRa divided by K phi. Then we can notice that the speed decreased with the armature current increase, but practically due to the armature reaction, flux decreased with the increase in armature current, and hence the speed decreased slightly. Then for the torque versus speed, we substitute T developed equals to K phi Ia into the omega m equals to Vs minus IaRa divided by K phi, and we will get the relationship between the omega m and also the T developed. As flux is assumed constant, the speed decreased with developed torque increase, but practically due to the armature reaction, flux decreased with increase in armature current, and hence the speed decreased slightly also. Thus, at heavy loads, the motor speed is almost constant. Next, we can referring the graph using the formula P equals to T developed omega. There is a changing point between the constant torque and also the constant power in the graph, which is called the best speed omega best. Then, at the constant torque, the power increased with the speed increase. At the constant power, the torque decreased as the speed increased. That's all from me for the torque speed characteristic. Thank you.
Now I will introduce few ways to control the DC motor speed. First is using armature voltage control. This method is applicable to separately excited motor and permanent magnet motor. For the shunt motor, varying the supply voltage is not an appropriate method of speed control because the field current and flux will varying with Vt, and the effect of increasing of both the armature supply voltage and the field current tend to offset one another. So this results in a little change in speed. So from the equation, omega equals to Vt over K, which is a constant, times with phi. So Speed is approximately proportional to the source voltage. So this means that higher the armature voltage produced, the higher the motor speed. Next is armature resistance control. This approach can be applied to all types of DC motor, which are shunt, separately excited DC motor, series connected DC motor, and permanent magnet DC motor. For separately excited DC motor, the speed can be controlled by placing a resistor in series with the armature. So when the total resistance RA increase, the torque will decrease and the speed will increase. However, this method is seldom used because it is less efficient due to the losses in the external armature resistance, and this method is waste too much energy. Last is varying the field flux to control the DC motor speed. The speed of either a shunt connected or a separately excited motor can be controlled by varying the field current. To adjust the field current, we can use a rheostat to control the current by changing the resistance of the circuit. So it means that if we want a high current, we can set a low resistance resistor for the rheostat. And this method is not appropriate for permanent magnet motor because permanent magnet motor have a constant flux, while in series connected motor, the field flux is same as the armature current, so it cannot be independently controlled. So for separately excited DC motor, since the field flux is proportional to the current, when we adjust the rheostats so that current increase, the field flux also will increase. Based on the equation, when flux increase, then the motor speed will decrease.
The application of separately excited DC motor are using as an attractor, which are attracted in train and also automotive traction application. Besides that, the separately excited DC motor also used for power and lighting purpose. The field and armature of separately excited DC motor are excited by two separate sources, so it has disadvantages, which are it requires a separate field supply, high acceleration cost, high current drawn, and heavy loads, and also low starting torque. That's all for our presentation about the separately excited DC motor. Thank you.